In this tutorial, we'll talk about nonlinear fitting, and we will use two examples. One is from problem 7, example 17.8 in your book, and the second one is a plus b sine x plus cx squared. So we will use both of these examples to elaborate nonlinear fitting, and we will use the linearization method that we developed in the class. So here are the x and y values that are given in the book in example 17.8. So if we plot these values, it looks like an exponential curve, you can see. And the book problem actually asks you to fit an exponential model into this, which is a quantity 1 minus exponent minus bx. So a and b are the parameters, and x is the values, and m is basically the model that we want to fit. So these are y values. And if you look at the method that actually requires you to take the derivative of this model with respect to all the parameters, that is derivative of m with respect to a and derivative of m with respect to b. And of course these two equations are also given in your book. But because the parameter a and b is going to be initialized at some value, and then every iteration it will be updated by a small amount until we get the minimum value of the least squared error. So the book asks us to initialize with a equal to 1 and b equal to 1, and we can define a vector of parameters which is called p, and it has both the parameters in it as a column vector. So let's define these a and b, and then we define our p vector, which is the initial. This is basically p0, p sub 0, the way we looked at in derived it in the class. Now we can also find, for this p value, we can find out what the value of the function will be. So let's compare y and yf, and you can see that they are a little bit off, and we can plot both the observations and fit. So with these value of parameters 1 and 1, the model doesn't that well fit the data, as you can see. So what we end up doing is we end up creating a Z matrix and a D column vector, and look at your derivation from the class to see that Z is a column of the is a matrix where the first column is the derivative with respect to first parameter, and the second column is the derivative with respect to the second parameter calculated at the observation point. And similarly, D is the observations that we have minus the fit values for these values of the parameter. So y minus y fit. And once we have z and d, we can find u, which is basically delta p. Let's call it dp. That's better. So this is dp, and then we can, once we compute dp, we can add that to the existing value of the dp, and let's also print dp. So let's do the first iteration, and you can see that now the dp value was minus 0.27 and 0.5, and the new value of the parameter is 0.7285 and 1.5. So we started with 1, and the model has adjusted it to 0.72 and 1.5 by computing a dp. And now we can again calculate the fit value and plot this, and this is going to change, but notice how the values of these the locations of these red X will change as I plot the new updated value. So they have come actually below our observation points. And similarly, we go through this iteration again. And in this case, now P has been updated a little bit more. So P has increased to 0.79, it was 0.72, and similarly the second value of parameter has also increased from 1.5 to 1.69, and so we can again plot, we can again compute the new fit based on these new values of the parameter and now plot it, and again notice how this will change some of these red points to new location, and they have gotten closer for these values of the parameter. So as you can see, I have put this in a for loop even though I'm doing it manually. You can see how this updates one step at a time, and this converges to an exponential fit into the data, which is a nonlinear fit. So let's do one more iteration and see what happens, and see how the error has reduced, the dp has reduced even to 0.0008, which is very small value. And if you look at p, it's pretty much the same as it was the last time. And now I'm going to call these together and see it didn't change much. So it looks like we have started to converge to an exponential fit to the data. So now in order to run this code, I will run this, make it a script. So I'm going to let's look at the last part here. So instead of plotting it as points, I'm now defining a function of x, which is basically saying take p1 and p2 and fit the model that we already have, and we define a function that's a function of x in terms of the two parameters p1 and p2, and then we just run our usual code, the easy plot, and overplot our data points, and you can see this is the exponential fit into the data points that we have. And to show you, I will just put a return command here, which basically say after completing the function stop. But a new command that you haven't used yet is a pause command. So every time it plots here, it will pause the function and wait for you to press any key to continue. So let's save it and let's run it. So here is the first iteration, and now you have to go to the console and just press any key or press enter, and you will see it will go to the next iteration. It'll display the error or display the update as described in the for loop, and again if you press enter again, it'll go through the next iteration, and you can see how this has improved. And you can keep pressing enter. It will run through this code 5 times, and you will see the error has gone down to 1,000th, and then if I in the 5th iteration it has gone down to 10 to the power minus 5, which is very small, and then it shows us the line fit. Now I have down below another function, which is the b plus a plus b sine x plus c x squared. So this is a sine wave on top of a parabola. So let's quickly go through this code, which is very similar to the previous code. And in this case, here are the xy values. So you can see that if you were seeing this kind of data points, clearly a straight line is not a good model fit into this data. So let's try this a plus b sine x plus c x squared. So again, I'm initializing all the 3 parameters with 1, 1, 1 values and creating the vector. And then I'm going to run this loop which has a pause command in it. So it will pause, it has pause after the first iteration. As you can see, the red dots are significantly away from our data points, or red X's are significantly off the observation points. So once you press enter, it will go to the second loop, and as you can see in the second iteration, it has pretty much captured the points. Third iteration, our error has reduced to 10 to the power minus 13, so we are very close to the actual value. And now we can define the function and use the easy plot and plot command to look at our final fit, and you can see it very well captures the locations of the data points using this model. And this is how we can do a nonlinear fit into observation points.